class, section 1.4 is a first look at sets and set operations on sets. So you have seen a little bit of set theory in college algebra, and you saw quite a bit more in finite, but now we're going to dive even deeper with this math class, and we'll build upon the previous two. So the first thing I want us to know is that a set is a collection of objects, and the objects are called the elements of our set. We typically use capital letters to represent sets. So for example, here is, I need a proofreader. Here is the set A equals JK element OP. And we would say that P is an element of A, and we write it like this. This like sideways E means element of. Now because B is not an element in the set A, we would say B is not an element in A. So that's this element of symbol with a line through it. Another thing about set is that every set needs to be well defined, right? It needs to be well defined so we can determine what are the elements of that set. So for example, if C was the set of primary colors, I know that contains blue and yellow and red. And I know for a fact that doesn't contain green because green happens when you mix blue and yellow. Another thing is that all elements in a set must be distinct so that we can tell them apart. I wouldn't want to have 1/2 and 2/4, right? Are those the same? Are they different? They are the same, so we wouldn't want to have those. It's also important that each element in our set occurs only once, and that within the set, the order of the elements doesn't matter. So if I have the set 1, 2, 3, that's the same as the set 2, 1, 3, or 3, 1, 3, right? We've learned about permutations before. There's lots of ways I can write this, but those are all defined the same set. Two sets are said to be equal if A equals B, if and only if they have the exact same elements. And if two sets are not equal, we write A does not equal B, okay? So the set of even numbers would be equivalent to the set of 2 times the natural numbers, right? Because if I took all my natural numbers, which are 1, 2, 3, maybe we say positive, even positive numbers, right? That'd be 2 times 1, which is 2, 2 times 2, which is 4, right? This would be all the even numbers. So these sets would be the same. The universal set is the fixed set from which all set members are selected, and we usually denote this U. So U could be the alphabet, right? If we were looking at subsets of letters, U could be the real numbers. It depends on what you are looking at. The set with no elements would be called the empty set. We've talked about the empty set before. Sometimes you guys use that to represent no solution. And that's when we have a 0 with a line through it. That represents the empty set. That's the set of no elements, which seems kind of counterintuitive, but is very useful in set theory. So when I write sets, there's a lot of different ways I can describe the elements in a set. So one way is to list all the elements in the set. This works great for finite sets. Remember, finite sets have a countable number of objects. An example of a finite set would be B, C, D, E, F, G, right? I can count all the elements in that set. Another finite set would be the alphabet. I could list all the sets in the alphabet. All the elements in the alphabet, like A, B, C, dot, 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 Z. That dot, dot, dot means you can kind of infer what the next elements are. Some infinite sets would be N. This is the natural numbers, right? The natural numbers start with 1. Those are what we also call our counting numbers. And Z, this stands for the integers. It's a little mathematical shortcut. The integers. And that's all negative natural numbers, 0. all additive inverses of the natural numbers. So that's like -1, -2, -3, 0, and our natural numbers. Now this is not possible for all sets, and for those sets we would need to use set builder notation. In set builder notation, we can define a set S by S equals X, where X is an element of U and X meets some property. So U is our universal set and P is a property that the element X satisfies. So let's let C be the set of all colors. To write the set of primary colors in P, in set builder notation, we would take P equals X, and X is an element of the set of all colors, and X is a primary color. Okay. We could also have B, let B be the set of all Beatles songs, and P be the set written by Paul McCartney. So then P would be all songs that are in the Beatles repertoire, but only as long as X is a song that Paul wrote. Those are some examples of set builder notation. A set X is a subset of a set Y if every element in X is also an element of Y. Okay? We write this X contained in Y, and that's how I read it, X is contained in Y. If X doesn't equal Y, then this is said to be a proper subset. Couple things to note. 1, the empty set is a subset of every set, and every set is a subset of itself. So let's let A equal 1, 2, 3, and B equal 1, 2, 3, 4. So in this case, A is contained in B because all the elements in A are also in B. Okay? A is a proper subset because A doesn't equal B. It's important to note that A is contained in A because all of the elements in A are in A, and the same thing holds true for B. Like I said, every set is a subset of itself. The empty set is also a subset of A and a subset of B. The power set of a set A is the set of all possible subsets of A. A set with n elements will have 2 to the n subsets. So let's take a look at this. Let's let A equal 6. So the power set of A is all possible subsets of A, which are going to be 6, which is A itself, and the empty set. So this has 2 elements. So because A has 1, element, the power set of A has 2 to the 1, which is 2 elements. Let's take a look at if I had 2 elements in a subset. Then the power set of C, denoted with a big capital P, right? The power set of C is C itself, the element 3, which doesn't get a comma because it's by itself, the subset 2, so it's not just the element 3, it's the subset 3, and then the empty set. So because C has 2 elements, the power set has 2 to the n elements, which is 4. So why don't we go ahead and do the example right here where B is 5, 6, 7, and I want to find all possible subsets of B. So one of the possible subsets would be 5, 6, 7. I could then take all subsets of size 2, 5, 6, 5, 7, 6, 7. Remember, order doesn't matter in subsets. I could take all sets of size 1, and then the empty set. So because B has 3 elements, P of B, which is defined by this list here, right? If I put commas between them all, P of B has 2 to the 3, which is 8 elements. And I wrote the answer for you in the PowerPoint, so if I didn't get you the video and you were just going through the PowerPoint, you'd see the answer to some examples. So, like the power set, which is a set of sets, sets can contain both individual elements and sets, okay? It is then necessary to be careful when stating which elements belong in a given set. So let's let S equal 1, 2, 3, the set of element 2, the set of element 3, the set 4, 5, and the set 1, 2. I want to go ahead and determine whether the following elements are in S. Okay, so is 2 an element of S? Yes, it is. Is the set of 2 an element of S? Yes, it is. Is 3 an element of S? Yes, it is. Is the subset of 3 an element of 3? Yes, it is. Is 4 an element of S? No, it's not. The set 4, 5 is an element of S. And is 1, 2 a element of S? Yes, it is. One more example, is the element 1, the subset of just 1, an element of S? No, it is not. Now here for these answers, you're going to see that in this example, I took out the element 3, and I did that because I wanted to make sure you guys would see that if I took 3 out, it's not an element of S. So I'm sorry that this set is different than the first one. I'm going to go ahead and fix that for you guys in the PowerPoint that I will be posting.